Right, welcome everyone and good morning. We welcome you all to the first ever virtual CMAS conference. And to kick us off today, we're honored to have UNC Chapel Hill's Vice Chancellor for Research, Professor Terry Magnuson. Terry is the KM and Van L. Weatherspoon Eminent Distinguished Professor of Genetics, and also as the Vice Chancellor for Research, leads the university's $1.2 billion research enterprise. And with that, I will turn it over to Terry.
Thanks, Mike, and good morning, everybody, and welcome to today's symposium. This is the 19th anniversary of the Community Modeling and Analysis Systems Center, known as CMAS, that Mike referred to. This marks a milestone representing community collaboration towards the benefit of society. The CMAS Center has been hosted by the Institute for the Environment of UNC Chapel Hill since 2003. This annual conference really has been a hub that brings together national and international experts on air quality science, policy, and applications. So we welcome the more than 300 participants that represent academia, industry, consulting groups, and state and federal governments. A special welcome to our 60 international attendees from 18 foreign countries. This year's conference is being convened virtually for the first time ever, with 4 plenary panels with keynote talks and 9 sessions with over 120 presentations, and a new virtual social hour for community engagement. I want to extend a special thanks to the CMAS External Advisory Committee. This is a group of 13 scientists that represent different factions of the community, and that's regulatory, academia, and industry. And they act as an advisory committee to the CMAS director. I also want to thank the US EPA for giving UNC the opportunity to continue this program since 2003. And also thanks to all of you, the community, for your active participation, support, and interest, which is fundamental to the success of CMAS. The CMAS team has done an outstanding job year over year by supporting community-based air quality modeling. CMAS is an approach to the development, application, and analysis of environmental models that leverages the complementary talents and resources of the modeling community in order to set new standards for quality in science and in the reliability of application of technology. So this year's program is as exciting as ever, and I convey the university's best wishes for a successful conference. So with this short welcome and introduction, I now turn the conference over to Saurav, I believe.
Thank you, Terry, for your kind comments. And with that, we'll get started. Okay, so what I will do in the next few minutes is to provide a brief state of the status at the UNC for this Center for Community Modeling Analysis System. Of course, as you heard Terry mention, this is the 19th year of the CMAS Center serving the community. The CMAS Center at UNC was established in 2001. The US EPA CMAS Center was starting to host at UNC since 2003. This CMAS Center works with the agency to lead the international open source community-based air quality modeling analysis software used to develop policies and analyze air quality impacts. The objectives, threefold: to serve as a bridge between segments of the air quality modeling community, to foster the growth of the developer and user communities, and finally to serve as a hub for the modeling, education, and training. The functions of the CMAS Center are fourfold: to do model research and development collaboratively with the EP and the broader research community, to provide user support. This is a very active area of the center's activities, to provide growing support for a very large user community, to provide applications and training of the CMAS supported software, and finally to provide outreach. One specific example of where the CMAS type tools are used are, so this is the 30th anniversary of the Clean Air Act amendments. And this was a specific analysis that the US EPA did a few years ago, which shows the costs and benefits of the Clean Air Act amendments of 1990. And what this shows is based upon proposed controls and regulations based on the Clean Air Act amendments, you will have a large benefits compared to the cost. And this particular analysis showed that the benefits exceed costs by a factor of more than 30 to 1. Okay, there's a lot of details that goes into this analysis and there's extensive documentation. But the key point I want to make by way of these numbers is show that the tools supported by the CMAS Center are central to this analytical framework that allows EPA and the states and other agencies to do this kind of analysis, to look at the costs versus benefits of various regulations and the implementation of the national ambient air quality standards. So the overall toolkit, the framework looks as follows. The SMOKE and CMAC are two of the key models that most of us are probably familiar with. SMOKE is the emissions processing software, CMAC is the air quality model. So you bring in emissions inventories and emissions control measures through the cost framework, and then bring in meteorology from the former MM5 or the more recent current WRF, the weather research forecast model, through a preprocessor. And these concentrations are then propagated through constant response functions of the BenMap model, which provides health and economic benefits. So this is a very broad analytical framework that is used to do the kind of analysis that's summarized on the previous slide. Okay. So in the 19th year of operation, the CMAS Center is now serving over 10,000 users globally. So specific tools, as I mentioned very briefly on the previous slide, CMAC is the community multi-scale air quality modeling system. That's a regional scale model, followed by SMOKE, which is the sparse matrix operated kernel emissions modeling system, which is a preprocessor for CMAC to prepare emissions inputs. Then we have local scale dispersion models to model dispersion of near source releases, starting with the R-line model. This is a research line source dispersion model. Then two web-based versions of these models, C-line, the community line source model, and C-port, the community port model to model port-related emissions. And then various models for the architecture, design, and coupling of the various models, including IO API. This is the input-output applications programming interface, MSIP, or the meteorology chemistry interface processor, spatial allocator, speciation tool, and FESC, or the fertilizer emission scenario tool. Continuing on, for analysis and visualization, we have Verdi, the visualization environment for rich data interpretation, and its predecessor, PAVE, or the package for analysis and visualization for environmental data, which now is deprecated, but I mentioned because I do know a few people still using PAVE for analyzing, visualizing CMAC outputs. For model evaluation, it's AMET. This is the atmospheric model evaluation tool. And then for policy and planning, you have the control strategy tool, or COST, the emissions modeling framework, which brings together all the systems in a Java-based environment for tracking scenarios and performing various scenarios modeling. BenMap, the benefits mapping analysis program. And finally, the Abacus, the air benefit and cost and assessment system. So here is the global footprint of the CMAS community. So this particular plot shows two different pieces of information. One is the strength of the community across various countries. That is one showed in color codes from deep blue to yellow. And then you have the attendees at this year's event for the 2020 conference, the 19th annual conference, to see where we have attendees from. Of course, besides a very strong presence from North America, US and Canada, you have attendees from Europe, from Asia, as well as from South America. South America seems to be a growing part of the CMAS community, and we welcome attendees from all over the world. As I mentioned in the last year's briefing, the CMAS Discourse Forum is a very active area of avenue for us to support the community, where we have very targeted way of allowing the community to ask questions in terms of where they have need for particular data sets or access to specific tools or how to use a specific tool. And we get somewhere between 15 to 20 tickets or so per month. I call them tickets. These are help questions. And we collaboratively work both with the EPA and the CMAS staff to support the community by answering these questions. and allowing the community to proceed further with their own research and other needs for their particular initiatives. The CMAS data warehouse, this has been another area of activity from the CMAS Center using Dataverse. Dataverse is an open source web application to share, preserve, cite, explore, analyze data. But the key is researchers who provide data through Dataverse are given credit, academic credit, and have visibility for the data sets. Each Dataverse entry is linked to a unique DOI, enabling easy citation and discovery. And we have an open access database for collecting, disseminating model data from meteorology to emissions to air quality, inputs and outputs. Dataverse itself does not contain the data files. It's, however, keeping track of the data to providing detailed meta information about the data sets. All the data is stored on UNC's portal to the Google Cloud. And this is an activity we started about 2 years ago as a public service by the CMAS Center in close collaboration with the US EPA's Office of Research and Development and Office of Air and Radiation. So here is the overall sort of a flowchart of how data works within the data warehouse. We have the various data from emissions to meteorology to air quality observations. These are tagged through the Dataverse for generating DOIs and metadata. Then these are stored on the Google Cloud, the data warehouse. And from there, we enable reporting, modeling, and visualization. Some of these specific capabilities for interactive analysis is in the works, but right now users can download data from the data warehouse directly for their own needs. And this is a very rapidly growing resource. We have 33 some terabytes of data so far on the Google Cloud, and this is growing as we speak. So to summarize on the data warehouse, please think of this as a resource both for the community and from the community. What this means is from the CMAS community working with the EPA, we have data outputs, CMAC outputs hourly and daily for about 15 years at 12-kilometer resolution for the continental US. Emissions inventories for the most two recent modeling platforms, 2014 and 2016, and CMAC ready inputs using the latest version of the model, CMAC 5.3, at 12-kilometer for the CONUS. MSIP or the meteorology data for 3 different years at a 12-kilometer resolution, and more importantly, the CMAC Northern Hemispheric model outputs for the year 2016 at a somewhat coarser resolution of 108 kilometers for regional scale, but finer resolution when you think of global scale models. But these are allowed for users to download and extract initial boundary conditions to drive their own model applications for any part of the Northern Hemisphere. And we have an interactive forms interface to share data sets from the researchers to others. So we encourage the community to share data sets from their own work to the CMAS community through this portal. So think of this as a give and take. We provide a lot of data sets from the US EPA through this resource, and we also encourage the community to share data to the rest of the community through this portal. A very recent initiative is trying to move CMAC onto a Singularity container as well as on the cloud. So we have an initial version of CMAC 5.3 on a Singularity container, and this is being tested on a few different environments as we speak. And please stay tuned for a version of this particular Singularity container for the community to use in the near term. And soon we will have CMAC on the cloud as a service. This will be validated on multiple vendor platforms, the more popular ones out there, and we'll have CMAC on the cloud as a service. Please stay tuned for these two updates coming to the user community within the next year. Model downloads, just to see where we are making most of the impact in terms of user demand and user support. On the left, you have the product downloads for the last fiscal year. You see that CMAC and Smoke, of course, are the two largest products that we have, several thousands of downloads. And you can see sort of the same information on the right shown as pie charts. So CMAC and Smoke are about 50% of the total downloads that we have, followed by other tools such as C-Tools, Verdi, and the remaining ones. Okay. We released 5 different models in the past fiscal year. We have the most recent version of CMAC 5.3.1 just released in the last week or so. Then we had Smoke 4.7 and Verdi released in beta recently. AMET version 1.4 was earlier in the last fiscal year, and then FESC version 1.4.1. Training. We have transitioned the CMAS Center's training completely to online even before the pandemic started. So we do this twice a year in spring and fall. In fact, this particular fall season, we finished the Smoke online training 2 weeks ago, and the CMAC online training is to be held next week. And we have over 16 or so users lined up from all over the world to take the CMAC training. Then we did conduct international training sessions all over the world. You can see the spread of the geography there in terms of where the trainings were conducted. And on top of that, we had special trainings, one each for the Python for air quality research and applications, and one on model interpretive analysis a few years ago. Collaboration, information sharing, this is central to the CMAS objectives. Of course, we have the CMAS conference. This year, it's being held virtually for the first time. But before this, we had 18 different editions held at Chapel Hill. It's a very popular event and people really like to come back and see each other. Unfortunately, we don't have the ability to see each other due to the pandemic. This is the first time being held virtually. But at the same time, I hope that the social hour we have planned later today will allow users to mingle a little bit in an informal manner and catch up with each other later today. Of course, we have had the CMAS conferences held outside the US, in Asia and in South America. There are 2 more being planned for CMAS Asia in May 2022, and then in South America in July 2021. We'll see how the pandemic holds, if we're able to do this in person or virtual, to be determined, but there are plans to hold these next 2 editions in 2021 and 2022. Webinars, this is a webinar series we started some time back, and we had 4 new webinars in the past fiscal year on various products and the science updates that we have from the CMAS community. Then we have the CMAS Visiting Scientist Program. We've had people from all over the world come and spend anywhere from a few weeks to several months here with us at UNC, trying to work with the CMAS Center staff at UNC, as well as working with the EPA scientists on various topics of interest. And then peer-reviewed journal articles. We have had special issues from the CMAS conference on and off. The most recent edition is the version of the conference from last year, which was select papers from last year's conference were invited to be published in the Journal of Air and Waste Management Association. And these have gone through peer review, and the special issue will be released next month. So the next month's edition of the Journal of Air and Waste Management Association will have a special issue from the CMAS 2019 conference. With that, I want to recognize the CMAS Center team here at UNC. Of course, Dr. Adel Hanna is the director and also responsible for outreach, and followed by, for training and conference, BH Back, user support and documentation, Liz Adams, communications and events, Brian Ness and Emily Williams. I'm sure you've seen a lot of communication from us. Thanks to Brian and Emily. Technical editing by Kurt Thurber. I want to recognize the entire team for the exemplary job that they've all undertaken over the years to contribute to the success of the CMAS Center. And I also want to thank the External Advisory Committee. I want to recognize them from the community. I can see the list of the EAC members. I want to thank the EAC for their service to the community. With that, let me wrap up by thanking Dr. Adel Hanna. He's the CMAS director, for his contributions to the CMAS Center and his leadership over the years. I want to thank the CMAS community, which is you all who are listening to this particular talk at this conference, and for those who could not make it today, and to the EAC members I listed on the previous slide. The US EPA for the very active collaboration and contributions to the success of the CMAS Center, and of course for the funding. And Tom Pierce, who's the CMAS Center Program Officer from US EPA ORD. I also want to take a moment to recognize the conference team who helped put this together. BH Back, Brian Ness of UNC, the session chairs. We invited a lot of members of the CMAS community to serve as session chairs. I want to recognize and thank each of you for stepping up to serve as session chair and help us put this fantastic event together. And also a whole bunch of student volunteers from UNC-CH who did a lot of background work, and you'll see them in action through this week. And I want to thank them all for their contributions. And thank you. And we will take questions later. For now, I want to transition to Mike Peeler.
Thank you very much, Saurabh, and thank you so much for that incredible update. And what I'm going to talk about next is something that is akin to that incredible update times almost 20. And that is reflecting back on the fantastic career and leadership that Adel Hanna has provided for this program over the many years. Saurabh alluded to 2003 as being the date that the center and the other activities around the air modeling transitioned to the Institute for the Environment with Adel Hanna at the helm. We are grateful for his leadership and the incredible work he's done in building this community and all of the service around it. And it's bittersweet, but with excitement that I'm going to announce now that Adel is going to be transitioning into retirement, a well-earned retirement after an amazing career. And so we are grateful for all of the things that he has provided to the Institute for the Environment as a member of our team, to the university as reflected by Dr. Magnuson's presence today. The university holds this program in high regard. And also I know to the community, all of you who are here. So I thank you, Adel. I'm grateful for all that you have done and grateful for your helping us as we move into this transition. And from here, I'd like to turn it over to Saurav to have a little more conversation about the great things you've done, and thank you.
Thank you, Mike. Adel, I want to congratulate you on your retirement. You have been an incredible leader, both for IECMPD as well as for the CMAS Center. You have been an inspiration for the CMAS team at UNC during this past nearly 2 decades. Okay? You have left an indelible mark on the community, not in the US, but all over the world. I fondly cherish, Adel, the various trips we have made over the years, sprinkling the CMAS pixie dust, I must say, far and wide, from countries in Asia, specifically India and Korea, to South America and Brazil. I'll remember the various conversations, Adel, over the years and how you have thought about how to continue and foster the growth of the CMAS Center. You've been an amazing leader, Adel. And one particular style I want to call out is your style of being sort of a little bit hands-off to allow people to grow and bring up their own ideas. I think that's been very, very exciting and inspirational. I want to thank you and wish you the best, Adel, in your retirement, and hope to catch up with you on and off as you unwind from the incredibly hard work and the amazing career you've had over the years. Thank you. With that, I want to invite Tom Pierce. Tom is the US EPA Project Officer for the CMAS Center. I invite Tom to address the community, please.
Thank you, Sarah. Over the past 2 decades, for this 1 week in October, like many of you in the audience, I've entered the doors of the Friday Center and was soon greeted by the kind and caring face of Adel Hanna. Indeed, when you think of CMAS, Adel is the first person that comes to mind, as well as he should be, since Adel has been the leader of CMAS since its inception. As pointed out by my colleague Rohit Mathur, who is one of the founders of CMAC, Adel played a key role in promoting the C, or community, in CMAS. Adel helped to develop a comprehensive training program. He grew a community of several thousand worldwide users, many of whom are in the audience today. He fostered in-house research to support the evolution of CMAC. He organized and promoted this highly successful annual conference, which is now a major venue for discussing advances in air quality modeling. It's also a unique forum to discuss issues at the nexus of air quality research and regulations. He's also spearheaded special issues in scientific journals that bolstered the scientific reputation of the CMAS conference. As was pointed out, Adel constituted an external advisory committee to remain attuned to the needs of a diverse user community, which includes federal and state agencies, the public and private sector, academia, as well as international users. And it's in this vein that Ken Shear, who is now retired, reflected that CMAS has had numerous stakeholders, not all of them in friendly terms with each other. Adel was the ultimate diplomat, knowing just the right words and offered the right suggestions at the right time to ensure harmony and continued success of CMAS. As such, ST Rao, the former director of our division, ST noted that Adel is a kind and thorough gentleman to the core, and I could not agree more, Adel. Adel, speaking on behalf of all your friends and colleagues at EPA, both current and retired, we thank you for your leadership of CMAS over the past 20 years, and we wish you all the best in your well-deserved retirement. Sir?
Thank you, Tom.
Thank you, Tom.
You're welcome.
That was wonderful. Thank you, Tom. I agree with each and every one of your words. This is just amazing. Adel, would you like to address the community?
Yes, thank you, sir. Thank you, Vice Chancellor Magnuson, Director Pillar, and Mr. Tom Pierce and Dr. Saurav for your kind words and remarks and for hosting this tribute to me. It is my pleasure and honor to receive this tribute on my name. I would like to say that I have enjoyed every minute working with the CMAS at UNC This project will remain in my heart even after I retire. CMAS at UNC gave me the opportunity to work very closely with esteemed scientists at EPA, scientists who developed the smoke and the CMAC and many utilities tools that benefit the community. And I appreciate that very much. Most important, CMAS could not be a CMAS today without the support and the hard work of my colleagues at UNC, namely Dr. Sarav Arnshalam, Dr. B.H. Peak, Ms. Liz Adams, Mr. Brian Ness, Ms. Dang Mei Wang, Dr. Frank Minkowski, and Dr. Carly Coates, and many others who are not anymore with the UNC. They went to other jobs, like Mr. Zach Edelman, who is now executive director at LATCO, and Dr. Uma Shankar, Dr. Aijun Chu, and others. I would like to say, especially for Zach, that he was instrumental in developing the famous CMAS training program that crossed the border, as Dr. Arshan mentioned, in reaching out toward scientists in Asia and in Europe and all over the world. At the same time, I will not forget to acknowledge two late EPA scientists that played a big role in developing the CMAC model and activities. Those are the late Dr. Daiwan Bayan and the late Dr. Jeff Young. Both were shared the development of the CMAC model. Finally, I would like to thank UNC-IE administrative support for their hard work. Dr. Susan Cohen, Ms. Susan Frassesi, and other members of the administrative staff. Thanks for those who put this conference together, as Dr. Arshan mentioned. Great job, and thanks, best wishes to colleagues, and thanks to the whole community for making UNC and EPA appreciate the work that they have been doing all over the years. And thank you, and I wish you good luck and God bless. Sarah.
Thank you, Adel. We wish you the best, and congratulations again on your retirement. But I do hope to see you at future events. I hope that the future events will be not virtual and we'll be able to see you in person. And hopefully we'll see you at the receptions and such, Adel. Thank you, and enjoy your retirement.
Thank you very much, Sarah.
With that, I'm going to invite Dr. BH back to give a brief overview of the logistics for the rest of the conference this week. BH?
Thank you, Sarah. Good morning, everyone. Congratulations, Adel. I just want to say thank you for all your leadership over the years, and we'll miss you.
Thank you, BH.
Enjoy your retirement. So today, briefly, I just wanted to kind of go over this year's CMAS conference. So as you know, it's quite different than any other years we have the CMAS conference. There will be no live presentation, as you know. It's only pre-recorded presentation is available, and we sort it by each session. So please go and check out those pre-recorded sessions about all the presenters. And also optionally, you can download this PDF version of their presentation slide. So then you can kind of go through it and see whether is something that you want to watch those pre-recorded session. Some of the, I know each session, the pre-recording presentation is 15 to 20 minutes, so not everybody has all the time to read everything, but there's one option you can go through the slide if you want to. And also, because this is a remote conference, we wanted to make sure the user may have questions for the specific questions to a certain presentation. We created this Google form integrated into this, the site. So you can actually submit your question to a certain presentation you have question about. So you can still put that question through there today. Later this afternoon, we will close the Google form, but until then you can submit those questions through there, so that we will compile those questions and then send them to to the session chair, so then they can use that information to go over their live Q&A webinar session in the Tuesday, Wednesday, and Thursday. Now, of course, if you didn't have a chance to put that question out and you didn't have time to watch all the pre-recording before the Q&A session in Tuesday, and Wednesday, and Thursday, please just join it, and then you can also ask any questions during the 1 hour each live Q&A sessions. Next one is, as you're here, but the keynote speaker is we distribute in 2 days, Monday and Friday. Each day have a 2 session. It's 11 to 12:30, and then brief 30-minute break for your lunch, and then after that 1 to 2:30 p.m. there's a nice keynote speaker we line up for you. So please come and enjoy the talks. And also all talks in Zoom webinar will be recorded, will be posted on the CMAS website later. So then someone who didn't join the call, wasn't able to join the call, or from the other side of the country, it's too late for them to join the call, please come and watch those pre-recorded versions later after the session is over. Another thing is, because it's a remote, conference, we wanted to give you a little bit of chance of in-person conference experience. So we did create this new thing called CMAS Social. It's today, 3 to 4 p.m. You have to sign up, and then once you sign up, you'll get the Zoom link that you can come in, and then we will allow you to kind of randomly put in the 6 people Zoom breakout room. Most of you are familiar with this breakout room, and you will get a chance to meet someone that you never really, maybe someone you already know, so maybe you don't. This is kind of more like when you're walking in the hallway in this Friday Center, you run into someone you want to talk to. That's the kind of chance that we want to simulate that experience for you. And the last one is the Tuesday and Wednesday, Thursday, there's a 3-hour long session. So there's a 3 live Q&A webinar session per day. So each day there's 11 a.m. to 12 noon, and then 12:30 to 1:30, and 2 to 3. There's a 30-minute break between, and total 9 live Q&A sessions available for you to come and join. Just to make a note that the remote sensing and the machine learning 2 sessions has been merged as one. So there's a total 10 session there, but the live Q&A session is only, there's 9 of them. So please come join. Each session consists of 2 live the session chairs, and all presenters will invite them as a panelist, so then they can be available to answer any questions. And then also there will be a moderator who can monitor any live question may come through that during the session. So the live Q&A webinar session, how it's gonna proceed is gonna be, they will receive this pre-submitted the Q&A session, the questions from you guys, and then we'll give those lists to the session chairs, and the session chair will go over those questions one by one, and then panelists will be able to answer those questions. And then during the live session, if there's any question you may have, you can submit it to the live Q&A module that is built into this Zoom meeting. Please ask questions. We have a moderator to help you to transfer that question to session chair to answer for you. And if there's any time is left, there's a discretion to the session chairs. They can actually create their own session-specific discussion forum if there's time is allowed. And then also those questions, all those live sessions are pre-recorded, will be posted on the website. So then later on, you guys can watch it later. Thank you, Sarah.
Thank you, BH. That was a fun summary. Thanks for putting this together and helping the attendees to see what to expect over the next few days. Thank you, BH. Okay, let's move on. It's my distinct pleasure to invite Professor Barbara Turpin from UNC's Department of Environmental Sciences and Engineering to address us next. I first want to acknowledge and recognize Barbara for accepting my invitation when I wrote to her a few weeks ago. She immediately responded, and I was delighted to get her consent to come and speak to us and address the CMAS community. By way of introduction, Barbara Turpin is a department chair and professor of environmental sciences engineering at the University of North Carolina, Chapel Hill. She combines lab experiments, chemical modeling, and field research to improve our understanding of linkages between air pollutant emissions and subsequent human exposure. Her research interests include indoor chemistry and secondary organic aerosol formation through aqueous chemistry. Professor Turpin received a BS from the California Institute of Technology and a PhD from the OGI at the Oregon Health Sciences University. She conducted postdoctoral research at the University of Minnesota's Particle Technology Laboratory and was a professor at Rutgers, go Scarlet Knights, Barbara, for 20 years before joining the University of North Carolina. She's a fellow of the American Association of the Advancement of Science, of the American Geophysical Union, and of the American Association for Aerosol Research. Professor Turpin is also a past president of the American Association of Aerosol Research. She is currently an associate editor of the journal Environmental Science and Technology, ESNT. Dr. Turpin is a recipient of the Atmospheric Environment's Hagen-Smith Prize in the year 2009 and AAAR's Sinclair Award in 2010, and the American Chemical Society's Award for Creative Advances in Environmental Science and Technology in the year 2018. Please welcome Professor Barbara Turpin.
Thank you. Thank you, Saurav. Let's see. So today I'm going to talk about critical public health challenges that call for our community's engagement. So how can atmospheric chemists and engineers help address our most pressing problems? So first, I want to welcome you to Chapel Hill and to the 2020 CMAS conference. And I'd like to really first acknowledge that this has been a really trying year, and that the COVID-19 pandemic, which is responsible for over 1 million deaths annually and 200,000 in the US, has, is an ongoing challenge for all of us. My heart goes out to all of those who have lost loved ones and any who have lost jobs. This pandemic is really life-changing for many, and it affects us all. Its disproportionate impact on marginalized communities, both locally and globally, will be long-lasting and multifaceted. This is the Department of Environmental Sciences and Engineering's centennial year. So I've been thinking a lot about how environmental scientists and engineers, and specifically atmospheric chemists, can best address our most pressing public health problems. Our department is kind of unique. We're one of the founding members of the Gillings School of Global Public Health. And we're the first engineering department in a school of public health. There really are only 2 at this point. Increasingly, environmental scientists and engineers are responding to and planning for and working to mitigate new and evolving environmental and public health threats. Threats that are often both global and local, and threats that have a disproportionate impact on marginalized communities. Threats whose solutions require both depth of knowledge and the ability to learn from and teach each other, and to work creatively in interdisciplinary spaces and across difference. Threats whose solutions, and this includes the pandemic and climate change, benefit from, maybe even require, global cooperation, anti-racist thinking, and integrated holistic solutions. Now, health motivates many of the goals in the United States National Academy's report on environmental engineering in the 21st century. These goals are really focused on healthy and sustainable living on our planet. The environment and the atmosphere, specifically, feature prominently in the World Health Organization's top global health threats. Climate change has taken the top billing in both of the last 2 years. And climate change also contributes to fragile and vulnerable settings, drought and crop failures, conflict and migration, and in some cases, infectious diseases. Air pollution makes this list and contributes to non-communicable diseases like heart attacks and pathogens, which are sometimes airborne, like COVID, and protecting people from dangerous products like PFAS. Oddly, there's only a slight hint about the importance of fairness to health. Structural barriers to fairness have a major and negative impact on public health in the United States, and undoubtedly elsewhere as well. Marginalized communities tend to have higher environmental exposures and occupational exposures, and less resilience to the adverse effects of extreme events. And some of these reasons are intergenerational. So Princeville, that I'm showing right here, after it was flooded by Hurricane Matthew, Princeville is the first town in the United States founded by freed people after the Civil War. It was founded in 1885. The first residents of Princeville were looking for land ownership, economic independence, and control over their own lives. The only place available for them to live was this low, swampy area on the south bank of the Tar River, and it has flooded many times. The UNC's Department of Environmental Sciences and Engineering was founded 100 years ago because of poor management of water and sanitation. And that poor management of water and sanitation was causing infectious disease outbreaks in Chapel Hill and in towns across the state. This problem was exacerbated by legal segregation and disparate services for white and Black citizens, and by a lack of political power by Black citizens to improve their services because of barriers put in place to keep them from voting. Black residents had marginal educational and job opportunities, and a lack of inherited land, wealth, or credit that they could use to leverage, to invest in their future. So who's heard of Elizabeth Cotten, a famous folk singer from Chapel Hill? Her story was pretty typical. She was 27 in 1921 when ESE was founded. She had to leave school at age 9 to help support her family. She worked as a domestic in someone else's home, making 75 cents a month. She worked as a domestic into her 60s when her musical talent was accidentally discovered and changed her life considerably. My point is that life was very hard for Black residents 100 years ago. And those initial conditions have cast a long shadow on public health in North Carolina and much of the United States. The story is different in different countries, but many places, I'm sure, have large disparities within their population. So 20 years before ESC was founded, the story really starts with water, but I promise I'm getting to air. 20 years before ESE was founded, engineers at UNC had built water and sewer systems to serve the UNC Chapel Hill campus and the east part of Chapel Hill, where the white residents lived. But it took many years before Black residents in Chapel Hill were served. In the meantime, they were drawing well water that was contaminated by nearby latrines. And this had major consequences for the health of Black residents. And it adversely affected the health of the entire town. So disparities affected, really impacted the ability of the town and of the state of North Carolina to address public health issues. Over the course of ESE's 100-year history, our faculty and alumni and many others across the country have made major contributions to advance the safety and reliability of the US water and wastewater systems. This work was enabled in part, an important part, by nearly 50 years of EPA regulation. And this work has had a major positive impact on public health. But despite the progress, substantial disparities in water access and water quality continue in the US today, in part because of this legacy of segregation, redlining, and of gerrymandering of town boundaries, which was really done to control who could vote in towns. And these things, as I said, these continue to impact water access and water quality and health today. 43 million Americans, about 13% of the population, rely on unregulated private wells for drinking water. A study by Jackie McDonald Gibson concludes that children in homes relying on private wells have a 25% increased odds of elevated blood lead compared to children in homes served by community water systems regulated under the Safe Drinking Water Act. Private wells serve many rural residents in North Carolina. Among the urban and suburban North Carolina residents, African Americans are disproportionately served by unregulated private well water. So disposal decisions about coal ash result in part of our energy choices. And the manufacturing of PFAS are both major issues for North Carolina residents relying on well water. Atmospheric chemists have an opportunity to influence the course of these activities because energy generation decisions are influenced by air quality and climate considerations. And because the atmosphere plays an important role in local PFAS contamination and perhaps also global PFAS transport. So per and polyfluoroalkyl substances, PFAS, are heat resistant and water and stain repellent chemicals that are used in industrial and consumer products. I'm certain that they're in your house. They're persistent and bioaccumulative and carcinogenic and immunosuppressant. And they're manufactured many places, and one of those is the Chemours plant in Fayetteville, North Carolina. Chemours has been dumping PFAS effluents into the Cape Fear River for decades. But over the last couple years, residents living near this plant in Fayetteville, the plant's right here, have discovered that their well water is contaminated with PFAS. And this contamination is mostly in this direction, southwest and northeast of the plant. And the groundwater flow couldn't explain this. It just doesn't go that way. So DEQ scratched their heads and then they put out buckets and they collected rainwater. And they found high concentrations of Gen X. This is the concentrations of Gen X in the rainwater along the prevailing wind directions from the plant. And they found that they were quite high. Well, actually, they put out buckets all around the plant, and they found that the concentrations were quite high along the prevailing wind direction, suggesting that the atmospheric deposition is, perhaps the source of contamination for those private wells. We've measured PFOS at much lower concentrations, but across North Carolina. And even though the production of PFOS was banned in the US 20 years ago, we see significant concentrations. We really don't know where this comes from. Some of it could come from long distance transport from China, where PFOS is still being produced. But the differences in concentration across the site suggests that there are some much more local sources. So you can see the highest concentrations are observed in the summer here in Wilmington and Research Triangle Park. There could be local primary atmospheric sources, perhaps associated with PFAS waste streams. People buy a lot of products, including from China, where PFOS may be still contained in the products. So it's possible that somehow, because of those the waste streams from municipal areas could be a source of PFAS. Photochemistry can also alter PFAS composition. And we know that the Cape Fear River has brought substantial contamination of PFAS in the ocean near Wilmington. We know that PFAS likes to accumulate at the surface, at the ocean surface, and that bubble bursting and wave breaking can be a source of PFAS to the atmosphere, including PFOS. This is a local and a global issue. There you go, there's my cartoon I forgot to show you. PFAS has been found in the Arctic, including in snow. So how much of a role does the atmosphere play in global transport of this forever class of compounds? What are the major atmospheric sources and transformations? What actions will be effective in the management of PFAS? And, why do we keep making chemicals and using them before we understand the implications? This is the 50th anniversary of US EPA and the Clean Air Act. The Clean Air Act has been very successful in reducing emissions of criteria pollution, even while energy consumption and population and vehicle miles traveled and gross domestic product in the US have increased. This has led to major positive impacts on US air quality and visibility, quality of life and health. And it's right for us to celebrate these tremendous achievements on EPA's 50th anniversary year. These advances have been made in part through decades of progress, understanding atmospheric chemistry, and generations of predictive chemical transport models. It's also important to remember that there are tremendous differences in air quality across the world and within our own populations. Many of the world's largest cities are very polluted still, with 9 out of 10 people breathing unhealthy air. And poor and marginalized communities frequently have disproportionately high exposure and less resilience to adverse effects of extreme events. such as displacement due to flooding, drought-induced wildfires, and crop failures. Because of the fuels they use, because of the neighborhoods they live in, because of the jobs they have, and the resources they can draw from to recover from disasters. The two top public health threats of 2020 are both global and local. One of these, of course, is COVID-19, and Glenn Morrison will talk more about this later in the week. We know that when infected people talk and sing and cough, they generate expiratory aerosols and droplets that contain the CoV-2 virus. They create a plume of particles in front of their face, and the concentrations of the virus are highest in that plume within a few feet of their face. The large droplets fall rapidly. That's what the six-foot rule is really designed to do, is to keep you out of away so you don't, somehow let these large droplets hit you in the face. But it also keeps you out of that high concentration plume. And then those particles then just mix throughout the room. So the submicron aerosol particles remain in the room. They really don't deposit very fast at all until they leave with air exchange. So people are at especially high risk of infection when they spend time indoors, close together, with many other people because of the increased chance that somebody is infected and doesn't know it. For an extended period of time, because your dose depends not only on the concentration, but the time, exposure time, and especially in poor ventilation locations, and especially in locations where people do not wear masks. Air quality modeling skills can contribute to exposure and risk assessment and help provide options for reducing, optimal options for reducing risk. These assessments can even include time activity information by using anonymized cell phone records, which are now available for research. This work benefits from interdisciplinary teams. Here's an example. These are some examples of teams from ESE. And of course, there are people all over the world working hard on this. Interdisciplinary teams, including people that understand the community and the settings and the behaviors, as well as aerosol transport and microbiology and public health. Addressing this pandemic benefits from, and maybe even requires, both global cooperation and local action. Climate change is the #1 long-term public health threat. The excess energy trapped in the Earth's system as a result of greenhouse gases raises the Earth's average temperature and increases sea levels, putting many of the Earth's largest cities at risk. It raises sea surface temperatures, resulting in more powerful hurricanes with higher storm surges that carry more moisture and cause increased flooding and spread contaminants like hog waste, complete with its antibiotic-resistant bacteria, and arsenic from coal ash ponds. It changes atmospheric circulation and precipitation patterns. It causes droughts and floods, heat waves, extreme weather events, which in turn impact air and water resources, toxic releases, food and nutrition, infectious and non-communicable diseases, and migration and conflict pressure. Climate change exacerbates health inequities because of differences in proximity to industrial contaminants and because of differences in, who lives in low-lying areas, differences in household resources available to recover from crises, and differences in healthcare access. Addressing climate change and designing a sustainable future are major focus areas in the National Academy's report on environmental engineering for the 21st century. And success in building public health resilience to climate change requires global cooperation and calls for taking an equity lens. Well, these are people from ESE working on these topics. Of course, we need pretty much everybody to work on these topics, and many, many of us are. Atmospheric chemists, experimentalists, and modelers are needed to develop innovative methods to better estimate methane emissions, to understand and account for the interactive effects of emissions and air quality on climate, and climate on emissions and air quality, to characterize atmospheric transformations, exposures, and health risks from wildfire emissions, and to design effective policy solutions with co-benefits for health and climate. We can do a lot more in this area. We need solutions that take a holistic accounting of the public health costs and benefits of energy, food, urban planning, and transportation planning decisions. And by working with public health and community partners, atmospheric chemists have the opportunity to do this in a way that will advance health equity. In fact, I'd argue that we really can't address public health without considering health equity. Thank you very much. And for the opportunity to share with you.
Thank you, Barbara. That was a very broad spectrum. Thanks for taking us through from water pollution to air, from indoor to outdoor to climate and health. I mean, that's a super broad spectrum. Thank you for giving this very broad perspective and the challenges that we have. Okay, as questions are coming up on the Q&A board, I encourage the community to please type your questions on the Q&A board. I did have one question as I think coming up. This was on your PFAS slide, Barbara, on the particle phase. So you had the numbers from different parts of the state, and you alluded to transport. I was thinking about the relative roles of transport versus local production from that Chemours facility that you talked about.
Okay, so from Chemours itself, let's see. Yeah, so there, let me just show you the map here. Maybe it's helpful to see. So transport from Chemours itself, there are quite a few different PFAS compounds that are emitted from the Chemours facility. And of course, some of them are in the gas phase and some of them are particle phase compounds. And so, I'm not sure that there has been that much modeling of transport. The compounds, the gas phase compounds, PFAS are pretty water soluble. And so wet deposition is going to be an important loss process from the atmosphere. But I think that we have several pathways by which PFAS from a manufacturing plant can end up, that people can end up exposed to them, right? So, PFAS emissions directly from the stack, then you can model that transport in the downwind directions, right? Probably a couple of the big limitations are just understanding the partitioning parameters for these very strange compounds. What is their Henry's law constant? How do they partition into aerosols or stay in the gas phase? We know something about oxidation and photolysis. For example, these FTOH compounds can photolyze and make PFOA, which then will end up in the particle phase, right? So there are some photochemical transformation processes that take place. But there's a fair amount of debate about how does this material from the production facilities end up in places, in remote places like the Arctic. To what degree does it come from places like China and North Carolina? There's a lot more emitted in China than in North Carolina. To what extent does it come through the atmosphere? And to what extent, there's kind of an active debate about the relative importance of global transport through the atmosphere and through the oceans, right? We know that, other things happen as well. Like we buy a lot of products from China, and some of those products have PFAS in them. And so when we use those products in our home, there's a possible emission in our home, right? And the waste streams from urban areas have PFAS in them. So you find PFAS in the wastewater treatment plants. If you buy, stain resistant, I love those blouses that don't wrinkle. And stain resistant clothes or water repellent clothes, and you wash them in your washing machine, you're probably contaminating your water with PFAS, and that ends up in the wastewater treatment plant. If we take municipal waste and we burn it, do we destroy these PFAS compounds completely when we do that or not, right? So concentrations, places where they've measured PFAS in the air, in indoor and outdoor air, have found concentrations indoors to be about 10 times higher than concentration outdoors. So homes could be a source of PFAS to the atmosphere as well, right? And then, contaminated water, as I mentioned, can be a source to the atmosphere. So there was a paper published that was suggesting that PFAS could be transported across the world in the oceans and then come up, end up in particles through bubble bursting. We don't need it to be transported from China to North Carolina for that to happen, because the Cape Fear River is so contaminated that there's plenty of PFAS in the ocean right here. And bubble bursting and wave breaking can put that back up into the atmosphere. So I think there's a lot going on. It's there's really a need to better understand the partitioning of PFAS and the physiochemical properties, so we can do a better job of modeling.
Thank you, Barbara. Questions have started to come up on the Q&A board. The first one, I believe, is from Tesh Rao. PFAS has been around for some time, but for it to come to the public forefront as far as the public health issue goes, has taken some time. Any comments on other contaminants might be around that will cause more widespread public health concern in the near future? Is there any way we can guess at what other such public health issues from air emissions perspective are lurking?
Yeah, I mean, I think, in my opinion, and I'm a scientist, not a regulator, but it really bothers me the way that we handle new chemicals. I think the precautionary principle is a good one, and we don't use that here in the United States. So, our approach seems to be more around, we're making new chemicals all the time, and then we decide later if it was a bad idea or not. And, so I don't like that approach. I wish we did it differently. I wish that we learned more about compounds like PFAS before we started using them. But I think I'd like to give a shout out to Julia Reger, who's on our faculty. There are other people doing this kind of thing too, but there's a lot of value in using computational toxicology, especially computational toxicology around mixtures, and using computational toxicology and exposure information to prioritize which compounds do we need to study more, do we need to focus on from a standpoint of better understanding their toxicity and their health risk assessment. Because every year there's so many new chemicals being manufactured that we can't use animals and test all of them. So I think that the comp tox methods have great promise to help us deal with that. And EPA is working hard on these things, and some of the younger faculty who are skilled at both the toxicology and the, don't mind math, they like math. So I think that shows a lot of promise.
Thank you. Another one from Uma Shankar goes back to the transport versus chemistry. How reliable are the PFAS emissions characterized at this point, and so that we understand long-range transport versus chemistry modeling better?
Yeah, so I think that depends. I mean, the particular situation with Chemours, I think for decades, they did not understand their emissions that well. I mean, maybe I'm wrong about that and they're just pretending, but I think that may be true, that they didn't even understand their emissions that well. Either into the Cape Fear. They must have known that they were dumping a lot of stuff into the Cape Fear River, but I'm not sure they knew what it was exactly. And also their emissions into the air. The state of North Carolina, Department of Air Quality has really worked hard at making them, do that. So I think in the case of Chemours, we know a fair amount about the emissions now.
Okay, that's good to know. The next one is from Ben Murphy. He would like to ask if you could speculate a bit on our knowledge gap on the environmental science side of how the surfactant properties of PFAS. Certainly surfactants could be important for understanding CCN activation in PFAS plumes. The bubble bursting mechanism you mentioned too could be impacted by surface modification. So how large is the gap? Do you expect we will see wide variability among PFAS molecules? Or can we simplify the view somehow based on assumptions about PFAS as a class? Can we use information from manufacturers directly, or are bulk properties less meaningful in the context of PM?
Yeah, I think in the context of PM, the bulk properties are less meaningful. I think the PFAS that end up in the particle phase, and on the water surfaces, right? There are, the part of the challenge with PFAS is there are many different classes of PFAS compounds. So there are, there's many classes of compounds where a bunch of the hydrogens have been replaced with fluorines. That's what we're talking about. So some of them are carboxylic acids, and some are alcohols, and some are esters. Pretty much any kind of organic compound you can think of, and you take off a bunch of hydrogens and put on fluorines, and you'll find them, right? So, probably not all of those are great surfactants, but the carboxylic acids and the sulfonates seem to be very good surfactants. And so, I think the likelihood is that their surface active properties are really quite important in those cases.
Okay. The next question touches upon the breadth of the topic. Actually, you covered earlier, Bob, in your talk. The pandemic underscores the importance of research on indoor environmental conditions, temperature, humidity, ventilation, etc., and air quality, and their impact on public health. What do you see as the unique challenges and opportunities that connect these areas?
Yeah. So the biggest challenge, and I'm plugging Glenn Morrison's talk again later in the week, and you can get a lot more information about what we know and don't know and how well we can do this. I think there's opportunities for people who like to do the really detailed detailed modeling in indoor spaces. You know, obviously for COVID-19, the indoor environment has turned out to be really the major place where there's been infection and transmission. The challenge, one of the biggest challenges with working on indoor spaces is that everyone is different, right? And if you want to go do measurements, for example, you know, you could bring all kinds of fancy equipment to one home and you would really characterize that home, but then people would say, well, maybe that's just a really unusual home. You know, it's not very representative. Or you can bring, you know, you can buy 200 samplers and then put them in 200 different homes, but you're characterizing each home not very well. So from a measurement standpoint, that's a real challenge. I think that there's an opportunity to, you know, I guess the way I've approached indoor air chemistry measurement work is to do both of those things. You know, we've done some really big studies. We've done some studies with, you know, 10 or 20 homes where we make a bunch of measurements in 10 or 20 homes, but then we make those same measurements in one home with a bunch of real-time analyzers, right? And so we'll intensely characterize one home and put it in the context of a larger group of homes, right? Where we've made sort of integrated measurements or simpler measurements. So I think that kind of measurement approach is valuable. And if I go back to the first, you know, the biggest indoor air study that I've been involved in was the RIOPA study. In that case, when we designed that study, we weren't aiming to get a population distribution. We were aiming to make measurements across differences that would help us understand the dynamics, right? And understand what matters. So different climates, different air exchange rates, different ventilation and air conditioning practices, you know, different distances to local outdoor sources and things like that. And I think that was valuable also. So once, you know, with that kind of data, then I think, you know, we really do rely on modeling, right? You know, I think, you know, maybe residential modeling is easier in some ways because there's a lot of detail from the American Housing Survey and so forth that you can use, and information from EPA that you can use to help do residential modeling. But, you know, commercial modeling in commercial spaces, again, the biggest challenge is probably understanding the flow in the building and the ventilation, you know, and how that affects transport throughout the building. I don't know if Glenn will talk a little bit more about that perhaps later in the week.
Yeah, that particular panel is exchanging information now on making sure they all cover this. So that planning is happening as we speak, Barbara. That should be a good panel, and I encourage the CMAS community to tune in on Friday afternoon for that panel. Okay, I don't see any more questions from the community. I have one more for you, Barbara, from your talks earlier with the specifically going into aerosols and CMAC. I know we touched upon the COVID and indoor a little bit, but going back to ambient PM and CMAX treatment of ambient PM and aerosol formation. What do you see as the emerging areas of interest from a measurements perspective that's coming out from PM aerosol formation that are relevant for CMAC? Could you talk about a little bit?
Yeah, I think, you know, from my perspective, I think there's been a lot of work recently on multi-phase chemistry in aerosols, which is clearly important in aerosols, and some also in clouds, although I think that it's been harder in some ways to understand to what extent the cloud chemistry of organics matters, just because it's hard to, clouds, the transport is long and the reaction times are long and things like that. But one of the big, I think, really big uncertainties is about oxidant and radical formation in aerosols. You know, for example, we know that O singlet D and OH are produced in aerosols, you know, but we really don't have a very good idea of what the concentrations of aerosol phase oxidants and radicals are. And I think that is going to make, in both aerosols and clouds, and I think that is a really important uncertainty.
Thank you. I don't see any more questions. We are able to wrap up a few minutes early. Thank you, Barbara, for an amazing overview of the very broad spectrum of topics and giving people something to think about for research and taking the time to spend with us this morning. Thank you again. With that, we wrap up this particular session this morning, the opening session for the CMAS 19th Annual Conference. And we'll reconvene at 1 p.m. this afternoon. BH, any words from you for the 1 o'clock session?
Nope, I think it's good to go.
Okay, thank you all and have a wonderful rest of the day. We'll see you at 1.